Welcome to InterviewPro. In the previous video, we have seen how to find the closest binary search tree value for a given target. Today, let's see a continuation to that problem, closest binary search tree value 2. This is a LeetCode hard question which was asked in interviews for companies like Google, Amazon, and LinkedIn. Let's look at the problem statement. We will be given a binary search tree and a target. We will also be given how many closest values should we find for the given target. In this example, we are given this binary tree with the target 3.7 and the value of k is 2. So the two closest values would be 3 and 4. If you haven't watched my video on the closest binary search tree value, I recommend you to watch it before solving this problem. Just to recap, a binary search tree contains a root. All nodes towards the left of the root will be less than the root value, and all nodes towards the right of the root will be greater than the root value. This is applicable for all the subtrees. Before trying to solve this problem using a binary search tree, let's take a simple array with random values and a target 13. We have to find two closest values to 13. If we start from the first element, the difference between 13 and the first element 23 is 10. And the difference between the second element 12 and the target 13 is 1. So far our two closest values are 23 and 12. For the third element, 20 minus 13 is 7. So as per the question, we want only two closest values. Now we have 20, which is somewhat closer compared to 23. So the closer values are 20 and 12. Then we have 16, which is closer than 20. Then we have 15. And when we reach the element 10, which is at a distance of 3 from 13, we already have 15 and 12, which are better than 10, right? 15 is at a distance of 2 and 12 is at a distance of 1. These two are somewhat closer compared to 10, which is at a distance of 3. So our final output would be 15 and 12 are the closest values to 13. Let's apply the same logic to a sorted array as well. So now I have the array sorted. I have taken the same array, but now it's in the sorted order. So the first element is 10, which is at a distance of 3 from 13. 12 is at a distance of 1 from the target 13. So our first two closest values are 10 and 12. Then we'll move to 15, which is at a distance of 2. And what are our previous closest values? 10 and 12. Compared to 10, which is at a distance of 3, 15 is more closer, right? It's at a distance of 2 from 13. So I'll remove 10 from our closest values list and I'll add 15. Then we have 16, which is at a distance of 3. So there won't be any change to our closest array values. Then we have 20, the distance is 4, so no change. 23 is at a distance of 10, so our two closer values would still be 15 and 12. But did you observe one thing? There is one point where we could have stopped our comparison. As this is a sorted array, we know that the distance between target and the values in the array are going to increase as we move towards the end of the array. So it's not necessary to evaluate all these elements. We could have stopped it in the at a certain point. So keep this point in mind because we are going to apply this to our actual problem now. So we have this tree. This is a binary search tree, and we have already seen that a sorted list is giving us a better solution without the need to process all elements. So how do we get ordered list from a binary search tree? We can perform in-order traversal. So if we perform in-order traversal on this binary search tree, the output would be 1, 2, 3, 4, and 5. So let's start the in-order traversal. First, we'll move to the extreme left because this is how the in-order traversal works, right? It starts with the left, then moves to the parent or the root, and then it goes to the right. So we have 1, And what is our required number of closest values? It is 2. So let's take a queue to maintain our closest values. Why use a queue? You will understand it in a minute. First, add 1 to the queue. Move to the route as per in order traversal. The size of the queue was 1, which is less than k. So there is a place for one more element. So add 2 to the queue. Then we move to the right of 2. Our queue is already full. It is of size 2. We cannot accommodate one more element. So we have to make a decision here whether 3 is closest or not. If yes, how to add this to the queue. As we already know that in this queue, we follow first in first out approach. If we have to accommodate an element in the queue, we should remove the first element. So the distance of 3 to the target, which is 3.7, is 0.7. And the distance of the first element in the queue, 1, to the target, which is 3.7, is 2.7. So which is closer among 1 and 3? 3 is closest to the target, right? So we will be removing 1 and our queue will be having 2 and 3. And we move to the parent of this left subtree, which is 4. Now we again have the same situation. Our queue is full. It already has 2 and 3. The size of k is 2, so we can't add one more element to this queue. Now let's make a decision. What is the distance of 4 from the target? It's 0.3. And what is the distance of the first element in the queue from the target? It's 1.7. So it's clear that 4 is closer compared to 2. So remove 2 from the queue and add 4 to the queue. Now the queue will have 3 and 4. Then we move to the right of the binary search tree. We have the node 5. Then we have the same situation, make a decision. Now we see that the first element in the queue is closer to target compared to the current element. So we don't make any change to the queue. We have 5. This won't be entering into the queue. Next, we'll move to the next element. So consider if there are few more elements in this binary search tree. We have already seen an element 5. Any value as per the in order traversal, if there are few more nodes, the value after 5 would be greater than 5, right? So the distance from 5 to 3.7 is greater than the distance of first element in the queue from the target. So any element after 5 will also have a distance greater than 1.3, right? So is it necessary to evaluate all those elements? No, we can simply stop here. The point where first element of the queue is closer to the target compared to the current value will simply exit the loop and we return this queue. So our final answer would be 3 and 4. What did we do so far? We wanted to loop with the sorted data. So using in order traversal, we went to the extreme left and using queue, we started adding the closer elements. When the queue is full, we made a decision whether to add the current value to the queue or not. For the value to be closest, it has to be closer than the smallest value in the queue, which is the first element, right? So based on the distance to the target from the current value and from the first element in the queue, we removed the first element and added the current value. If the current value is farther from the target compared to the first element, we'll simply end our computation because we know that the nodes after the current value will obviously be farther from the target. Now let's see how we can put this in the code. This is our problem statement and I'll be coding in C#. Let's declare a queue first. Queue of integers. I'll simply call it queue. New queue of int. Then we need to perform in order traversal. How do we do that? We do that using a depth first search. So I'll create a method called DFS and I'll pass the root, target, k and also the q which we have created. Finally, what do we return? We'll return the elements from the queue. So q dot to list. Now let's define DFS function. Private void DFS. We have the same parameters like this. So let me copy it from here. And the extra parameter is the q and q. Now, okay, so here, when do we end this DFS? When we reach the end of the tree. What is the end of the tree? If root, or let me name this as node because this is not really a root. We will be performing recursion to each and every node. So node would be the better name here. So when the node is null, we'll simply return. Otherwise, we'll move to the extreme left recursively. So node dot left, and we'll pass similar parameters, target, k and q. Then we have to deal with the current value, which is node dot value. I'll comment it for now. Then we have to move to the right. Node dot right, comma, target, k and q. This is nothing but I have simply done the in order traversal code here. Now we need to add extra computation to deal with the parent node, right? So once we reach the extreme left, we have to check if the queue is available to add this node or not. So q dot count. If it is less than k, we can simply push it to the queue. So q dot nq of node dot value. If it is not available, that means if the queue is already full, what do we have to check? We have to check the distance from target to the current value and the distance from target to the first item in the queue. So first let me calculate the distance from target to node dot value, and then the distance from target to the first element of the queue. So I'll simply pick the first element of the queue. So if this value is less, so if the node value is closer to target compared to the first item of the queue, what did we do? We simply removed the first item of the queue and then pushed the current value to the queue. So I'll remove this q dot dq of q dot dq, sorry, and then we'll nq node dot val. If this condition is false, that means the current node value is farther from the target compared to the first item in the queue. So we can't add this item to the queue. And also it's not necessary to go through other nodes after the current value. So in our example, we saw that after at the node 5, this condition was false and we couldn't add this 5 to the queue. So we simply returned because any element after 5 in the in order traversal would be greater than 5. So it's waste of time to go through all those elements because they would obviously be farther from the target. So I'll simply return from here. Our DFS is ready. Okay, sorry, this has to be equal to null. We have to stop recursion when we reach the end of this node. So node equals null. Let me run this now. It is the test cases are passing. Let me submit, and our solution is accepted. Coming to the time complexity, In the worst case, if k value is equal to n, then our closest array, then the queue will have all the nodes from the binary search tree. So we have to traverse through all nodes in the binary search tree. So our time complexity is big O of n. And also the space complexity will be big O of n, because if k equals n, we have to store all elements in the queue. So the time complexity and space complexity both will be equal to big O of n. I hope the solution is clear. If you like the content, please like, share and subscribe to InterviewPro. Thank you.